With my big honor, let me introduce our next speaker today, Mikhailo Dokuchaev from Institute of Mathematics and Statistics, University of São Paulo, Brazil, who will tell us about twisted Steinberg algebras of not necessarily Hausdorff ample groupoids and regular inclusions. You're welcome.
Thank you, Oksana. Can you hear me? Okay, I will try to share my screen. Can you see my screen?
Great. Oh, it's great. Thank you very much.
I would like to start thanking the organizers for the invitation. It's a great honor and pleasure being with you. Also, a deep gratitude to the organizers for keep doing this, keep organizing this important series of conferences despite of the war, showing incredible strength. So I'm going to talk about a joint paper with Rui Axel from Federal University of Santa Catarina, Florianópolis, Brazil, and Hector Pinedo from the University of Santander, Bucaramanga, Colombia. And I will start with some basic notions. I will speak about groupoids, some topological groupoids. So we denote by G0 the set of unit elements of the groupoid. And each groupoid is a small category in which every morphism is an isomorphism, so it has objects. We will identify objects as the unit morphisms. So obviously, any morphism has a source, and you can and also has a range. So we consider the source map, sending each morphisms to its source, and the range map, sending each gamma, each morphisms to its range. We also denote by G2 the set of all composable morphisms, all composable elements of the groupoid. Also, we will use two important subsets. The first one are those morphisms which morphisms we can also see like arrows. So those arrows which are going down from a vertex and come back to the same vertex. They form a group which we call the isotropic group of the vertex X. Also, another set, all morphisms, all arrows going out from X. So obviously the isotropic group of X is a subset of this second set. Well, by an étal groupoid, we mean a topological groupoid whose unit space is the unit space is the element of the object of the groupoid. As I said, we identify with all units, all unit morphisms. So we assume that the unit space is a locally compact in Hausdorff in the induced topology. And we also impose the conditions that R, the range map, is a local homeomorphism. This is equivalent of requiring that the source map is a local homeomorphism. It is known that in an étal groupoid, the unit space is an open subset. You can find it in a paper by Axel, for example. We will be interested in those étal groupoids which are ample. And an étal groupoid is called ample if it has a basis formed by compact open bisections. So let me just come back. I skipped the important definition of a bisection. So a subset of the groupoid is a bisection if we restrict the source map on this subset and is injective. Also, the restriction of the range map is also injective. So we can see bisections as arrows going in parallel. Two arrows may not have the same source, and two arrows are not allowed to have the same range. We say that the ethyl groupoid is ample if it has bases formed by compact open bisections. K will be a field. So the idea to give a construction of an algebra related to an ample groupoid, which are generalization of the so-called Steinberg algebras. So these are more general Steinberg algebras. We call them Twisted Steinberg algebras. And for this purpose, we introduce the notion of an algebraic Feld bundle. Feld bundle, this terminology comes from sister algebras. A Feld bundle is a set E such that we have a surjective map from E to the groupoid. We have, so fixing gamma from the groupoid, we consider pi inverse gamma, and we call this set the fiber over gamma. And this fiber over gamma is supposed to be a vector space. Also, we have a multiplication map. So we can multiply two elements from the capital E, from this bundle, if the pi of U and pi of V form a composable pair of morphism in the groupoid. And this multiplication is associative. It is bilinear, and also if you take a composable pair of morphisms, if you multiply the fiber over alpha by the fiber over beta, then the result is supposed to be in the fiber over alpha beta. Okay, so this is an algebraic bundle. And we also introduced the notion of a topological bundle. So an algebraic bundle is a topological bundle if E has a topology which is not necessarily Hausdorff, and such that pi, that surjective map onto the groupoid, is a local homeomorphism. Also, as I mentioned, each fiber is a vector space, so it has a zero element. And the set of all zero elements is a closed subset. We also call this set a zero section. It is supposed to be closed in the bundle. And addition is supposed to be continuous. So we naturally may add elements which are in the same fiber, right? Multiplication by scalars from K is also a continuous map, and the multiplication is also continuous. So this is a topological Feld bundle. Well, we are interested in line bundles. So a line bundles over the ethyl groupoid. G is a topological Feld bundle such that each fiber is a one-dimensional space, a vector space. And moreover, if you restrict the multiplication to the composable pair of fibers, then it should not be degenerate. It should be a zero map. So should not be a zero multiplication. So it is a non-degenerate in that sense. Examples of line bundles can be obtained using two cocycles of groupoids. We will consider the field. K is an arbitrary field, and we'll take discrete topology on this field. The definition of two cocycle is usual, so it's a map from the composable pairs of the groupoid into the non-zero elements of the field. It's a continuous map such that it is normalized in this sense, so the value of the cocycle on gamma and source gamma should be 1, and also on the range gamma, comma gamma also should be 1. And also it has to satisfy the usual cocycle identity written down multiplicatively, of course, assuming the alpha, beta, and beta gamma are composable. Now, given continuous to co-cycle over groupoid, we can construct the field bundle. We just take the product space, product topological space, and pi will be the projection of this on the second coordinate. So each fiber will have this form. Of course, it's obviously a k-vector space in a k-vector space in usual sense, and the multiplication is given as expected. So you take two composable elements from the bundle. So these are pairs in our case, T alpha and S beta. So necessarily alpha comma beta form a composable pair of elements of the groupoid. And we define the product as, so we multiply the field elements, we multiply the groupoid elements, but we also twist it by this co-cycle. So it's easy to check this really line bundle over groupoid. Now is if the co-cycle is identically equals to 1, then we call this bundle trivial. So we denote this bundle by E omega, and if omega is trivial co-cycle, then we shall say that this bundle is trivial. Now, by a twisted groupoid, we mean a pair, an étal groupoid and a line bundle over that. Moreover, we assume that this groupoid is ample. When we define bundles, it's enough to assume it's étal, but when we will speak about algebras, we need to assume that this is ample. So take any open subset of the groupoid, and a function from U to E is called the local section if the composition of pi with disk C is the identity map. So what is it? It is just the choice of representatives of fibers over U. So we consider only fibers over this open subset, and in each fiber we just choose a representative. So this is a section, local section, and if U is the entire groupoid, then we will call this a global section. Now we will focus on compact opal bisections. So we assume that our groupoid
so presumably you assume that Xi is continuous, right?
Not so far.
Not so far. Just arbitrary function. Just arbitrary function, right?
Yes, but we will use only continuous.
Right.
I will say it right now in the next line. Given a compact open bisection U in the groupoid, we denote by SU the set of all continuous, local sections. So that was a definition of local section, which is not necessarily continuous. I will use it maybe once, non-continuous, but we are really interested in continuous local sections, so that your question was perfectly posed. So we will consider all continuous local sections defined on U. Now we will extend this to the entire groupoid in the following way. So its value on the open set is naturally will be psi of gamma for any gamma from U. But if gamma is not in U, then we just declare it as the zero of that fiber, right? Each fiber is a vector space as zero. Now, it is important to know that this C tilde is not continuous in general. This is not really a surprise because Ben Steinberg defined Steinberg algebras of non-necessary Hausdorff groupoids, and he used continuous functions to define, to generate non-continuous ones, and those non-necessarily continuous ones form the algebra. But in any case, if G is Hausdorff, that's easy to see that C tilde is continuous. However, if G is not Hausdorff, then this C tilde may not be continuous. Now, given a twisted groupoid, we denote by the Steinberg algebra is going to be the linear subspace of all global sections, right? And those global sections not need to be continuous, which are spanned by the union of these sets. So we take all this C tilde and we take the linear span of them. And this is the Steinberg algebra, the twisted Steinberg algebra of the bundle. And all U run over the compact oval bisections of the groupoid. Well, we need a multiplication. So multiplication, the convolution rule, convolution formula. So the convolution product of two elements of this space so far, right? Calculated in gamma is this sum, where you take alpha, beta, all should be composable, right? Necessarily composable such that alpha, beta equal gamma. Then we show that this is really a well-defined map, and so that we have an associative algebra, which we call the twisted Steinberg algebra, associated to this twisted groupoid. Okay. Now, earlier notions, this term twisted Steinberg algebra was used already in this paper by Armstrong, Clark, Courtney, and McRomnick and Ramage of 2022, but the twist is the cocycle twist. So if we take this bundle of this form EW, where W is a continuous cocycle, then we get the algebra which is defined by them. So our algebra generalizes this twisted, two cocycle twisted algebras introduced by them. Also, if W is trivial, then we recover the original notion introduced by Steinberg. Actually, they were introduced in two papers by Steinberg, and also independently by Clark, Farthing, Sims, and Tom Forte. They announced it earlier, but published only in 2014. So we consider that they were introduced independently. Also, in Ben Steinberg paper, there is a theory of inducing modules, which we generalize. Some remarks. So this Steinberg algebra is not necessarily unital algebra, but it has local units. That means that for any element of the algebra, there is an idempotent E, such that the product E times F, F times E is F. Since we have a non-unital ring, we need to define what is a unital module. So it's a usual definition in algebra, in ring theory. So a module is called unital if R is non-necessarily unital ring, then a module V is called unital if RV equals V. And we assume that all modules are unital. By definition of the line bundle, if we take an x from a small x from the unit space, then it's easy to see this is going to be an algebra. And since it's one-dimensional, because our bundle is line bundle, it has to be isomorphic to K. Also, we use that non-degeneracy of the multiplication. Now, if we have a twisted groupoid, ample groupoid, we consider the restriction of this bundle over the unit space, right? And then we prove that this restriction to the unit space is isomorphic to a trivial bundle over the unit space, right? So it is a form of like E omega, or where omega is trivial. Now, any compact open subset of the unit space is trivially a compact open bisection. And it is easy to see that if you take a compact open subset of the unit space, then any continuous local section, so it takes values in fibers which are copies of K. But we can assume that they are just in the same field, and we can identify it with a function from the unit space into K, which is continuous, recalling that K has a discrete topology. And continuous in this setting means that it's a locally constant function, so that each point has an open neighborhood such that on that neighborhood it's going to be constant. This equivalent to be continuous. And we denote by LC G0 the set of all compactly supported locally constant functions of this form. So this small c refers to be compactly supported. And this, according to this identification, can be seen as a subalgebra of our Steinberg algebra. Now, let's fix a point in the unit space, and we will consider the restriction of the bundle to the isotropic group of this point. And so this is this restriction of the bundle. And it is, of course, a line bundle over the isotropic group. So let's denote it simply like A, Gx, comma E. Formally, instead of E, we should put this pi inverse of Gx, but we just simplify the notation. We show that this restriction of bundle on the isotropic group is isomorphic to a bundle of the form E omega for some two cocycle. And then it is easy to see that the algebra, so it's going to be a bundle over the isotropic group, so we can speak of the Steinberg algebra, right? And that is easy to understand. It's going to be simply the twisted group algebra. Twisted group algebra in the usual sense of ring theory, when you have a two cocycle of the group and you form the twisted group algebra. So the idea now to work between modules over the Steinberg algebra and this twisted group algebra, right? Now, we will induce modules, and for this we need a bimodule, right? So we have a fixed element of the unit space. So this bimodule is going to be the set of all finitely supported sections of the bundle restricted to this set. So let me recall that this set of all morphisms going out from the same vertex. And we transform this into a bimodule.
Can you explain what is finitely supported section?
Okay. So what is a support?
Support is
support is all elements such the value of the function on those elements is non-zero.
Non-zero, right.
So we assume that this set is support. That this support set is finite. Before we were assumed that this set is compact, okay, for compactly supported, but finitely supported, just this set is finite. Why finite? Because this is going to be discrete, right?
I see, yeah. Okay, thanks.
It has discrete topology, and compact means finite now. So we transform this into a bimodule. So it's left module of the Steinberg algebra and right module from that twisted group algebra, right? With the following actions. The actions are given by convolution. So you have this formula. It's simply convolution formula, right? For the left action, it's convolution formula, and also it is convolution formula for the right action. And so then we showed it's a bimodule. Now, in order to induce, we will tensor take any left module over the twisted group algebra, right? And we tensor it from the left by this tensoring, this inducing bimodule. So we obviously get a module of the Steinberg, left module of the Steinberg algebra, which we call the induced module. We also have the restriction process. So for this, again, fix a point from the unit space and then consider this ideal of all locally constant, compactly supported functions defined on the unit space, which whose value on this axis is 0. It's easy to see that's an ideal in this commutative algebra, right? These locally constant functions, they are a point-one multiplication of is a commutative algebra. And this is an ideal. So now taking a left module over the Steinberg algebra, we define the restriction the following way. We take all V from V such that JXV is 0. Then we show this is a module over the twisted group algebra. And we call it restriction relative to this point X. Now with this, I can announce our main results. So our first theorem said that suppose you have a twisted ample groupoid and let V be an irreducible module over the Steinberg algebra, irreducible left module. Assume that its restriction is non-zero for at least some point. So there is a point of the unit space that the restriction is non-zero. Then the restriction is an irreducible module over the skew group ring. And moreover, the initial module is induced from the restriction. Now, in order to have, we have a situation in which this condition is guaranteed. And this situation is follows. So let GE be as above, so that's twisted ample groupoid, and assume that V is a non-zero unital left module. All modules are unital, okay? Non-zero left module over the Steinberg algebra. Assume that it's finite dimensional over K. Then we show that there is a point of the unit space that is non-zero. So in particular, this about theorem is true for finite dimensional modules, for the modules which are finite dimensional over the space. And so in particular, any left module of the Steinberg algebra, which is finite dimensional over the space, or over finite dimensional space over the base field is induced from the restriction.
And the reason for the induce is simple because you have a groupoid, right?
Yeah.
Okay, thanks.
Now, next theorem. So again, let we have a twisted ample groupoid and take a left module over the skew group ring. Then this module is restriction of its induced module. Moreover, any submodule of the induced module is induced by a unique submodule of W. The induced module is irreducible if and only if W is irreducible, and it is indecomposable if and only if W is indecomposable. And finally, again, we have a twisted ample groupoid. We apply our result to ideals. So every ideal of this Steinberg algebra coincides with intersection of a family of annihilators of induced modules. And any primitive ideal of the Steinberg algebra coincides with annihilator of some induced module. So this last statement is not exactly what we would like to have, because we would like to show that induced, so that the module is irreducible, but we are not able to show it in general, only with some strong restrictions. So that's what I wanted to say. Thank you very much. Дякую за увагу і слава Україні.